So, welcome everybody to the second webinar of the Resilex project. I am Giulio Poggiaroni from ETA Florence, and today I will moderate this session. For those of you who are not familiar with the Resilex project, this is a project funded by Horizon Europe and is addressing the issue of supply of critical raw materials in Europe to be used in batteries and PV panels. And looking at these two technologies, the project also seeks to develop a new kind of solar panels and batteries that utilize different materials. So on this last point, we will focus on today's webinar. And before introducing our speaker, I remind you that you can use the Q&A box to post questions to the speakers, while I will post in the chat any other relevant information that are relevant for the project, like for instance, the project website and the link where you can download all the relevant information and reports that we have published so far. In particular, I would like to mention one report that was published last year on the availability of end-of-life solar panels that can be used to recycle precious materials, and other on the production, for instance, of ingots from recycled silicon. So, without further ado, I introduce the speakers for today, who are Laurie-Lou Senaud from CSEM, based in Switzerland, and Adeline Lanterne from CA, based in France. So welcome everybody. According to the agenda, we will go first with Laurie-Lou. So Laurie-Lou, you can bring up your presentation and start. Okay, we see your screen, but not the presentation.
I will just set up the slides. Okay.
Yeah, go ahead.
Yeah, okay. So thank you very much for the kind introductions. And let's start with the first presentation of today's webinar, which is about eco-design PV modules, bio-based materials investigations. And this presentation will share with you a part of the work performed at CSEM in the context of the European project Resilex. But first, here are a few words about CSEM, just to give you an overview of who we are. CSEM is a public-private non-profit Swiss technology innovation center. Our aim is to enable competitiveness through innovation by developing and transferring world-class technologies to industry. We are located in Switzerland with 6 different locations between Neuchâtel to Landquark. Our expertise is in many domains, and our DNA comes from the watchmaking roots. And from these roots, we are specialized in small, precise, and complex devices, as well as ultra-low power solutions. And our research and development effort focus on multidisciplinary approaches. Our different topics of research and development are organized in 3 different research priorities, which are the first one, digital technologies, precision manufacturing, and sustainable energy, which is the research priority of CSEM concerned by the presentation of today. More precisely, in the sustainable energy research activities, we are currently working and developing batteries, digital energy solutions, solar cells and modules, as well as integrated lightweight photovoltaics. So now, in the context of sustainable energy, CSEM is part of the European project Resilex, in which we are developing photovoltaic solar cells and modules. So nowadays, the photovoltaic technology is more than crucial for transitioning to lower environmental impact energy sources, as it allows for providing electricity with less than 5% of the greenhouse gas emission of coal power. However, even with the significantly lower environmental impact, it is not a net zero emission technologies, and ways to further reduce its impact are present at manufacturing and end-of-life levels. In this context, one of the main objectives of the Resilex project is to demonstrate sustainable eco-design PV cells and modules. And to illustrate this objective, here is a schematic of a PV module, which depicts all the different elements, materials, and components which are required to build a PV modules. We can see that many materials and elements are required, and for the Resilex project, we are investigating them at cell and module level to understand their environmental impact with the aim to decrease this negative impact. And more precisely, considering the PV module, the aim is to investigate eco-design and bio-based materials to replace the conventional ones and to study if and how it is possible to reduce their environmental impact. In this presentation, we will focus on components of PV modules. And in the second presentation of Adeline, the focus will be on the solar cells themselves. So to introduce the concept of eco-design PV modules, here is a graph presenting the environmental impact in terms of global warming potential for the complete bill of materials of conventional PV module, the one we are already on the market. And interestingly, we can see that the highest impacts are for the aluminum frame and for the glass component. And in addition, the backsheets and encapsulants present lower impacts, but they are based on oil and or fluor-based polymers. So with this in mind, our aim is to consider these elements and to investigate eco-design solutions to reduce the PV module environmental impact. So in our investigation, we consider the circular economic concept while aiming at keeping high reliability and efficiency of the PV modules. To share additional definition, bio-based materials are completely or partially derived from biomass, and they have the potential to decrease the dependence on fossil resources and to mitigate the associated environmental consequences. So based on this consideration, our work is to investigate if and which bio-based materials are suitable for PV and if their integration can be environmentally relevant. So in the following slides, the case of eco-design backsheet is detailed. So as presented previously, the glass presents one of the highest impact of the PV module, and one solution could be to replace it using polymer front sheet, but this requires to use a rigid backsheet for mechanical stability. And conventional backsheet present low environmental impact, but they are non-rigid materials, and they are made of multi-layers polymer PET fluor based, which means that they are oil-based, and the fluor is costly to treat and to manage during the end of life due to fluor emission and waste. So to remove the glass, the aim is then to develop eco-design rigid composite backsheet to replace conventional backsheet. And in this regard at CSEM, we are investigating bio-based backsheets made of flax composite and polypropylene. And in this case, the flax then is a bio-based materials, and the polypropylene can be biosourced. To investigate these materials, the first study was to implement the flax backsheet in conventional structure made of glass and backsheet to have a reference, and in lightweight structure than in the structure made of polymer front sheets and using the rigid flax backsheet allowing to remove the glass. For these two structures, it was possible to demonstrate a successful process integrating the flax backsheet with compatibility with other materials presenting no bubble and no cell breaking during the lamination process. We also perform reliability tests, and here the challenge is the low adhesion between the encapsulant and the backsheet. We demonstrate that the lamination interface was inside the composite itself at the polypropylene flax fiber interface. So here further investigation are required to improve the composite adhesion and could be performed. Based on this, we then perform additional reliability tests by performing damped and thermal cycling processes. The damped is critical to investigate humidity-sensitive solar cells technologies. And here, to pass the norm, the module needs to demonstrate lower than 5% of power loss after 1,000 hours. And the thermal cycling is critical to investigate the potential mismatch between thermal expansion coefficient of the different PV module components. And here the norm is passed for power loss lower than 5% after 200 cycles. With this test, you can see in the graph here that we demonstrated that lightweight PV modules integrating the flax backsheet present high reliability, similar to the conventional structure, which then integrate conventional backsheet. And for both damped and TC test, all the modules under investigation pass the norm, even 2 times the norm in damped here. And these are very promising results for the flax backsheet, which pass 1 time the norm in damped and TC, than for both conventional and lightweight structures. To go further, for development and based again on this result, we then decide to further investigate and improve even more our lightweight bill of material, still integrating the flax backsheet. Here, the aim was to further reduce the environmental impact while further improving the reliability. We thus built our lightweight modules using a non-fluorinated front sheet, which is developed by CSEM. Again, using the flax polypropylene backsheet, which was presented previously. And we also use encapsulant, which is also developed at CSEM. And in this case, the formulation of this encapsulant can be biosourced. And also, we decide to use 2 different types of solar cells technologies, which are the silicon heterojunction solar cells and IBC solar cells. Again, we put these modules in damped and TC test, and the result demonstrated that these modules are stable under TC and pass the norm in damped. But importantly here, the module with the silicon heterojunction solar cells pass below the norm after 1,500 hours, whereas the IBC are still stable after 2 times the norm. And then this illustrates that different solar cells technologies are impacted differently by humidity, which is also an important factor when we talk about the reliability of the modules. So in summary, these results are very promising and quite impressive as we demonstrate that the lightweight PV modules then integrated the 3 features, then the non-fluorinated front sheet, the CSEM encapsulant, and the flax backsheet pass the norm in TC and damped. So we demonstrate that in terms of reliability, flax backsheets are a promising solution. So now the second important step is to study its environmental impact and if it allows to decrease the environmental impact of conventional backsheet. So here is a graph showing the environmental impact of the CSEM lightweight here, which was presented previously, along with conventional glass and glass backsheet PV modules. So here the double glass modules present then the highest impact due to the glass contribution, and the CSEM lightweight module the lowest environmental impact. In this case, we can also observe that the flax backsheets present a higher impact in terms of CO2 equivalent than conventional backsheet. However, it provides the mechanical stability, allowing to remove the glass and thus reducing significantly the total PV module global warming potential. To complete and continue further this study, in-depth investigation of the different LCE impact categories is required in order to discuss and compare more precisely the conventional and flax backsheet. In addition, we need to note that also here the results are for module manufacturing, and that it is also important to study the module lifetime and end of life of the PV module in order to consider the impact of the module reliability. Indeed, when we are developing such eco-design solution, the challenge could be to find the best trade-off between long lifetime module and strong enough eco-design PV module bill of materials. So here, to conclude, it is important to keep in mind, based on this study, that environmental benefit of PV module with bio-based elements are not always guaranteed, and that require validations. To build a precise pictures, a holistic approach considering module performance, lifetime production, and end of life is required. We also highlight that removing the front glass of P module is significant to reduce its environmental impact, and that a promising solution is to use a rigid composite backsheet to bring mechanical stability. And in this regard, the flag backsheet demonstrate promising results, which are demonstration of a successful lamination process compatible with all other PV module components. The flags backsheets pass the norm in dampit and TC for both conventional and lightweight structures. And finally, it is a composite that allows to remove fluor, and the polypropylene can be biosourced. So to complete this study, the environmental impact of flag backsheet will be investigated in more details, especially by comparing the different impact categories to investigate their contribution in the total CO2 equivalent emission. So with that, that concludes the presentation of the first part of this webinar. So thank you very much for your attention, and we can take time at the end for a question and answer session. Thank you very much.
Thank you, Laurie-Lou. So perhaps since we have one question already, maybe we can try to answer this and then give the floor to Adeline. The question is, can you please talk about the new F3 front sheet that you developed?
The one with non-fluor, I imagine.
Yeah, probably.
Yeah, so here we are then developing the polymer solution. So we are developing all the formulation to make it, and it's possible for us to then either process it by external partner or to do it also at CSEM. But for the complete formulation, for the moment, it's still confidential. We cannot provide the complete formulation.
Okay, thank you very much. So now we can move on, and I will invite you, Adeline, to switch on the camera and then start sharing the presentation. In the meantime, I remind you to the attendees that I shared in the chat the link to the website of Resilex, where you can already download various documents and reports, and you can also watch the recording of the previous webinar, which was about the Critical Raw Materials Act and several other aspects. And on the website, you will also be able to rewatch the recording of this webinar. So I see that Adeline is ready, so the floor is yours.
Yes, thanks. Can you hear me? It's okay. Okay. Thank you, Julio. I'm going to try to discuss today about how we are trying to solve the indium challenge to reach sustainable silicon heterojunction solar cells at CEA and in the Resilex project. First, a few words about CEA. So it's a scientific and technology research player in France. Based on fundamental research, we are developing solutions in 4 main domains, which are low carbon energy, but also digital, future healthcare, and defense and security. And concerning renewable energy, we have a research institute for energy transition called LITEN, where we are developing new technologies to reach carbon neutrality by 2050. And our mission here is also to support industry in this sector in France and Europe. At LITEN, we are approximately 1,000 employees, and we are working on 12 platforms located in Grenoble campus and also in Chambéry at INES campus. And our main research area are photovoltaics, but also battery, hydrogen, and system grids, and also circular economy. I'm going to say just a few words about our solar platform at INES. It's a high efficiency photovoltaic platform. So we develop technologies there like heterojunction cells, but also TOPCon. And our mission here is to transfer this high TRL technology towards gigafactories and also to improve the sustainability of these technologies. We are also working on lower TRL technologies such as tandem of silicon and perovskite. And there our goal is to develop high efficiency cells on large area above 30%. And we also have at Ines a platform where we developed advanced and eco-design modules. Today, and to understand a bit our challenge to have a sustainable photovoltaics and solar cells fabrication, I'm coming back to what will be the place of photovoltaics in the world in 2050. If we look here at the roadmap from the net zero emission scenario from IEA, we see that they are planning a massive electrification of the energy sources from 20% today to above 50%, and that the solar energy parts here will have a fast increase and will be a major part of it in the end. And this corresponds to the installation of 14 terawatts of solar cells and modules. This is that I will call the low scenario because already the trend is already above this scenario. And we can also look at high scenario like ITR PV, more based on the photovoltaics market, and they are planning up to 60 terawatt of installation of photovoltaics. So this is what is planned, and today the current total installed capacity of photovoltaics is now of 1.6 terawatt, mainly in China. So we can see here the increase over the last years, and now in 2023 where we were. And this is done with new additional capacity installed each year. And we see here the dynamic of the production capacity, which is increasing every year. And in 2023, we have installed more than 400 gigawatts. But to reach now the targets and the scenarios that I talked before, this production capacity must increase further. And in the low scenario, we have to increase the production capacity up to 600 gigawatts per year, and in the high scenario, up to 2.3 terawatts. So this is also to reach that several solar cells technology will be used. And we can see here that the market share is divided between several technology, but all based on silicon wafer. We have a transfer currently of the PERC manufacturer towards the TOPCon technology here. And we also have silicon heterojunction cells, which are represents today 5% of the market share, and that should increase up to 20%. And we also see in a few years the tandems appear, so they are foreseen as the next steps here. Today I will focus on these heterojunction cells that will represent 20% of the market. This is a solar cell heterojunction structure. It's based on a silicon wafer. Then we have active layers on the top and rear, which are made of amorphous silicon. And then on the top of that, we have a transparent conductive oxide in blue on each side. And finally, we have the grid, metallic grid, which are there to contact the charges made of silver. This is a structure that can reach very high performances with large VOC value, and the record efficiency are above 26%. It's also a structure which is bifacial and which has a very high bifaciality coefficient. And it is processed at low temperature with very few steps. If we compare, like for example, here the carbon footprint for each technology, this is a module working in constants in this calculation. And for a heterojunction module of 22.4%, we see that we can have a low carbon footprint, mainly due and thanks to this very high bifaciality coefficient here. Also, it's a technology that which is compatible with very thin wafer, so we can reduce the wafer thickness and thus the use of silicon, which is a critical material. And also the wafer is responsible for a large part of the carbon footprint of the module. So when we reduce the wafer thickness here, we see that we have a strong impact on the total carbon footprint that is reduced by 20 kilogram of CO2 equivalent per watt peak for each 10 micrometers that we reduce in the wafer thickness. So in the end, it's a promising technology for a low environmental footprint with a possibility to reduce the silicon usage, but it's a technology which is using a large quantity of silver due to the fact that we are processing everything at low temperature. So this increases the cost, and also it's a technology that is using indium inside the transparent conductive oxide. So in the Resilex project, as Laurie-Lou mentioned before, we are trying to develop more sustainable solar cells and to improve the sustainability of heterojunction. And for that, we are working to strongly reduce the critical materials here, which are silver and indium. And also, we are trying to develop indium-free and silver-free heterojunction. So today I will only focus on the indium part. And why do we need indium? It's because of this transparent conductive oxide here. It's a layer that must fulfill many requirements. It's in charge to transfer the charges from the active layer toward the silver grid. So it must have a very high conductivity, also a low contact resistance with the silver grid and with the active layers below. And it must be transparent, so have very high transmittance. And it also must play the roles of an efficient anti-reflective layer so that the photon doesn't reflect on the cells. So this will determine its thickness. And finally, it also must have a good stability under humidity and under UV exposure. So nowadays, only indium-rich materials manage to fulfill all these requirements. And the mainstream is using 100 nanometers of indium tin oxide on both sides of the cells. So now why indium is a challenge to reach sustainable heterojunction is because it's a very limited production. So we see here that it's partly coming from primary and secondary production, but it's limited to 2,000 tons per year. Because it's a byproduct from other metals ores, and also it is used in other high value-added technologies such as LED or touchscreen. So its usage is in competition. And also for photovoltaics, we need quite large amounts. So this is what we are trying to calculate here. In standard heterojunction structure, we are using 100 nanometers of TCO, which represents between 4 to 6 milligram per watts of indium, which is represented here. And so if we want to limit the use of the global indium supplies below 20% of the world's global indium supply, then our production capacity of heterojunction is limited below 100 gigawatts per year. And so to reach the targeted annual production that I mentioned before, saying that here we have a technology that will represent 20% of the market, then this production capacity must go above 100 gigawatts. And to reach the target, we need to reduce indium by 70% at least. So in the community and photovoltaics research, there is many approach under studies right now to reduce or remove indium from these cells. And we are trying to work either on reducing the ITO thickness or working on indium-free TCO, so new materials, or a combination of both, and even low Tyrrell studies are trying to remove completely the TCO. And today I will present some results that we had on the Resilex project at CA, where we try to use very thin indium-based layers. And our goal there is to reduce the indium above 70% to keep similar efficiency of the cells than the reference, and also to have no impact on the reliability with these innovations. So first we worked on the front sides of the cells. So for there we reduced the ITO from 100 nanometers to 5 to 15 nanometers, combined with a new layers, which that I will call the double anti-reflective layers made of silicon nitride, because the very thin layers of ITO doesn't fulfill the requirements in anti-reflection. So we need an additional layers to have a good, a very low reflection on the cells. And so for that, we developed highly conductive thin ITO layers, and we also modify the layers below. So the active layers made of amorphous silicon were changed in order to reduce the requirements on the TCO. And also we had to validate that this double layer approach has no impact on the interconnection of the modules. And this is some results. Here you see some mini modules where we reduce the ITO from 1 nanometers to 5. And the efficiency of the modules are presented here. We see that we have actually similar efficiency than the reference for very thin ITO when we change the active layers. And this is also some module reliability tests that we performed. In the first part of the graph, we see how the module behave under UV treatment, and we could surprisingly see that this very thin ITO actually have enhanced the UV reliability. So we have lower losses for thin ITO in red here. And in the second part, it's how the module behave under humidity test. And then we see that 10 and 15 nanometers of ITO have similar behavior than the reference, but in red we have a very strong degradation, and so the 5 nanometers of ITO is unstable under humidity. And then we perform similar work on the rear side of the cells, and for that we worked on another indium-based TCO, which is an hydrogenated indium metal oxide, IMOH, and we reduce its thickness by 60% without having here, we see the module efficiency, we see that there was no impact on the module efficiency. However, the reflection and anti-reflective property of the rear side is modified, and so we have a reduction of the bifaciality coefficient. So here the module efficiency when it's illuminated on the back side, and we see a reduction here. And in the end, we combine these two approaches. So we combine the 50 nanometers of ITO on the front with 30 to 40 nanometers of IMOH on the rear. And by doing this, we have demonstrated and fabricated heterojunction cells with indium reduction up to 72% or 77% for IMO of 30 nanometers. And this is some solar cells characteristics with this very low indium content. What we can see that when we optimize and modified the underneath active layers, we can reduce the field factors losses and resistance losses of the cells. And we managed to have efficiency loss below 0.2% absolute with indium reduction of 77%. So this is okay, very good for us. And then we have wanted to test the reliability of this innovation in modules. So we fabricated some mini modules here in glass-glass configuration, and we performed the humidity test, this time up to 3,000 hours in 85 degrees and 80% relative humidity. And here you see the field factor losses through times for reference modules and for very low indium modules. We see that after 2000 hours in yellow, we start to see a higher sensitivity to humidity for the low indium heterojunction modules, which is increased at 3000 hours. But in overall, all the low indium module passed 3 times the standards, which is that you need to have a power loss below 5% after 3,000 hours under humidity. So in the end, we validate the reliability test. And so to summarize this talk, in this Resilex project and at CA, we have demonstrated the possibility to reduce indium in heterojunction up to 77%, having a very low impact on the cell efficiency and sometimes even no losses. The modules made with the cells are more sensitive to humidity, but passed for now 3 times the standards and have an enhanced behavior under UV. We also could show that with this innovation, we can increase the annual production capacity of heterojunction from 95 gigawatts per year at the beginning to more than 400 gigawatts per year. And now the next step with that is to confirm all these results in large-scale experiments to be ready for industrial transfer. And this is one way of reducing indium. There is other ones. And in the Resilex project, we are also trying to develop indium-free solution. And another next step is now to combine this with a very strong reduction of silver in the cells and to develop a silver-free metallization. Thank you for your attention. I also would like to thank all the financing from Resilex and Enel Green Power and the team. And now I think it's time for the question. I will give back the floor.
Thank you, Adeline, for the very nice presentation. So I'll give the attendee a few moments to think about possible questions. There were already 2 already posted. I just would like to show the attendees. This is the website of the Resilex project. Actually, here in the homepage, you can rewatch the previous webinar, and we will post this one here. Then in the results page, you find the documents I was referring to. We have a bunch of slides, the publication, including this report on the end-of-life panels, the availability of end-of-life solar panels in the coming years, and a few other interesting documents that go much more in detail on the results of the Resilex project, which will end in next year. Last but not least, here you have some updates from the project, and here in this policy platform webpage, you can fill in a survey about the usage and supply of critical raw materials. Actually, the input of this survey will help us drafting some guidelines that we will submit to the European Commission at the end of the project. So without further ado, looking at the Q&A box, there was, let me see, perhaps let's take this one for Adeline. Thank you for the presentation. Could you elaborate more on the process used for the IMOH fabrication?
From the IMO, we cannot give the full details of the IMO materials. It's a different one from the standard ITO, but it's also mainly made of indium. So it's very similar in composition, but it's a different indium metal oxide.
Okay, thank you very much. Then there is a question. In the sinks was deposited after metallization, like we can see the overlap of sinks with front side, silver contact as well. If so, is there any impact of sinks on silver resistance?
Yeah, no, there is no impact on the silver resistance. So in the process, it is deposited after the metallic grid. So we can wonder if there is an impact when it is deposited on the grid, but it has no impact on its resistance. the only thing is that we need to have a good interconnection with the modules and the ribbons after, but this is perfectly done. So so even if they have a thin dielectric deposited on the top, it's not impacted the module fabrication afterwards.
Okay, thank you very much. Then going back to Laurie-Lou, I mean, there is an add-on to the previous question. So the question we posed before was, can you please talk about the new F3 front sheet that you developed? You answered before, but then the attendee specified, but could you please state if it is PET-based, PET-based?
Yes, okay, it's a good question. You mean for the if it is PET-based for the polymer without fluor? That was a question because I don't see it on the chat.
No, it's in the Q&A box, not on the chat
Yeah,
box.
on the Q&A also.
Okay.
Okay, so the polymers which is fluor-free is also oil-based, but we're also working on the investigation to replace and make bio-based polymers, which is not so difficult to do because there is already many solutions to create polymer which is bio-based compared to oil-based, so many routes are already under investigations. But so that's a good question because when we are talking about eco-design and bio-based materials, we always have to think about the trade-off. Is it really essential to remove the oil? What is the most relevant to remove? Because in terms of CO2 equivalent, maybe we will not have such a significant gain. And also here, when we think about that, we need to go deeper in the LCA investigation and to compare the different impact categories. There is 16 of them. So maybe you can be worse in terms of water consumption, but you can also decrease the impact on the health of the people health. Then maybe sometimes you say, okay, in this place of the world, it's possible to maybe increase a little bit the consumption of water and then to drastically decrease the impact of the health of the people. So I think the complete discussion go further.
Okay, thank you. There is another one for you, I believe. Could you clarify if the flux backsheet affects PCE or if it has no impact on the solar cell as final performance?
Yeah, thank you, because it's also a good question. That means I didn't mention it, but there is then the lamination process to create the modules. Then we encapsulate the solar cells. And directly after encapsulation, we have similar efficiency, I mean similar power of the modules. And the solar cells keep the efficiency. So at this stage of the process, yeah, the efficiency are similar. And after the graph I presented in damped NTC, we can see the evolution of the efficiency when we have a lot of humidity, high temperatures, and so on. So here we can see that the efficiency of the solar cells then can be impacted if the bio-based backsheet is not resistant enough to protect the solar cells. But after lamination, yeah, the process was completely improved and optimized, and we have similar efficiency. And after we studied then the reliability under damped NTC.
Okay, thank you. There is another one. I believe it's for you. What is the recyclability difference between the conventional modules and the Resilex backsheet ones?
Yeah, can you just repeat the question?
Yeah, sorry.
Something that was not.
What is the recyclability difference between the conventional modules and the flux backsheet ones?
Okay. To give a full picture of that, I don't have all the details in mind, but for the recyclability, they are similar because for flax, then you can, I think, burn it like you can burn a conventional backsheet, and the differences will be on the emission, I think. But on that, I don't have the full pictures. I'm sorry. But I think it's a question for our partner in the Resilex project who can estimate these differences.
Okay, yeah, then I believe it will also be part of the upcoming results that we will disseminate. There's one question now for Adeline. Is it also possible to replace the cell grid with copper? Does this affect the thickness of the ITO layer?
Okay, yes, it's an interesting question because indium and TCO is a good a barrier towards copper diffusion through the silicon. And so, and we are trying in the Resilex project to replace silver by copper. And for now, we have first results where we actually used copper plating on this cell that we presented at the metallization workshop this year. And so we use copper plating on 15 nanometers of indium ITO, and this was working. So for now, our low indium content heterojunction seems compatible with copper metallization. But of course, if we want to go even lower or change the materials, the use of copper may have an impact on the TCO that we are selecting and on the TCO composition and thickness, meaning that this layer must be prevent and the diffusion of copper towards the silicon, because this is very this may impact very strongly the efficiency of the cells. So for now, it is working with the cell that I presented.
Okay, thank you very much. I don't see any other question, and in the meantime, I thank the attendees who have. No, there is one now. Is it expected within the project to integrate the two approaches described, so the bio-based backsheet plus low indium containing heterojunction, to build a prototypical cell module?
Yes, I don't know if you want to answer, Laurie-Lou, but it is not planned, but we will try, and I think so. Yeah, that's something we will try. I don't know if Laurie-Lou, you want to add something.
Yeah, that's if possible, we'll try, and also it's something we need to demonstrate in the project to see also if the bio-based PV module components are strong enough to protect an indium-less solar cells or indium-free solar cells, because here it's open also a lot of questions and way for investigations, because it will not be completely similar as the reference solar cells with full indium. So yes.
Okay, thank you very much. So we are at the end of our webinar. Thank you, Adeline and Laurie-Lou, for your very insightful presentation, and thank to the audience for their participation and interesting questions. I remind you that we will make available the recording and the slides soon on the Resilex website, and keep our channels monitored, because we will soon post some new documents, and especially a video about the production of silicon ingots out of recycled silicon. So thanks again to our speakers, and see you in the next webinar. Goodbye.
Goodbye. Thank you very much. Bye.
Bye.